Welcome to this course on digital VLSI testing. VLSI design, we know, is one of the very important part of system design, because the electronic system consists of IC chips, and these IC chips are fabricated by this VLSI manufacturing process. It includes from the specification till design and implementation. Out of all these phases, testing comes in one of the very important part of it, and in almost all the phases you will find some application of testing which is required and to get the system correctness ensured. During this course, we will be primarily looking into the digital VLSI testing, because knowing fully well that these integrated circuit chips, they can broadly be divided into two categories: analog circuits, analog chips, and digital chips. And of course, there are some chips which are mixed mode, having both analog and digital components. Out of this, digital VLSI testing is one of the very well grown domain, and over the years it has developed a lot, having a good number of strategies for testing, good number of algorithms, and the problems and how to address those problems. So, those all of them have become part of this digital VLSI testing. On the other hand, this analog testing is also popular, because to test analog chips we need them, but it is not that much developed as digital testing, and in many cases while testing analog chips, so we take help of these digital testing techniques for testing them. And of course, for mixed mode signal chips we have to do both analog and digital, both components are there. So, accordingly we have to test both the components, and many a times the algorithms that are used for digital testing, they are also used for analog testing. So, primarily we will focus on this digital testing part. So, in today's lecture we will be having an introduction to this VLSI testing. So, we will start with a general introduction. Then we will try to see in the VLSI design life cycle where exactly this testing lies. So, where at which phases we need this testing. Then for testing we need to apply some patterns, some test patterns are to be applied for a circuit to be tested or a chip to be tested. So, that requires some techniques by which we can generate the stimulus for the test operation. So, they are known as test generation techniques. Then in the VLSI chip that we have, so there can be many types of defects, like some of the points may be one point the line when the signal line was being drawn, it may be broken at some point, it may be shorted with some other line, it may be that some part has got some the silicon itself had some impurity. As a result, there is some problem, some defect that has grown, but this type of defects, so there can be innumerable types of defects, and possibly many of them are even unknown till today. But so, when we are trying to test a system against all those defects, it is very difficult to talk in terms of those defects. So, what we do instead is that we will talk in terms of faults. So, fault is the manifestation of the defect. So, if a line is if two lines are say shorted in the manufacturing process, so that actually gives rise to something known as a bridging fault. Similarly, if a line is broken in between, then depending upon the technology that we have, so that may be treated as a high point or logic high point, logic low point, or maybe a high impedance point, or maybe, so that way there can be many such types of faults that we can associate with these defects. So, instead of talking in terms of defects, so if we talk in terms of faults, it often makes the analysis simpler. So, we get a we can get good set of algorithms by which those faults can be attacked. So, they actually come under the broad heading of fault models. Then there are levels of abstraction, like whether we look at a system at the transistor level, which is the lowest one, or at the logic gate level, or maybe a combination of logic gates forming say RTL level modules like say adder, subtractor, multiplier, multiplexers like that, or even at a higher level when we talk in terms of a system where there may be a number of such chips put into a board. So, we talk in terms of board level, or maybe if we integrate all those chips onto a single silicon floor. So, all those designs onto a single silicon floor. So, we may get the entire PCB on a single chip, giving rise to system on chip type of architecture. So, that way at which level we are attacking these faults, at which level we are trying to address this fault. So, that gives rise to these levels of abstraction. So, it may be easy to attack the system behavior related faults at a much higher level compared to say at transistor level, whereas when we are talking about say individual lines being short or individual lines being open, it may be better that we talk at a much lower level. So, that way levels of abstraction will play a very important role in deciding which type of test technique we apply for the purpose. And there are several test technologies. So, we will also have an overview of the test technologies. So, this particular diagram, it shows how this VLSI design has become more and more complex over the years. So, in 1960s, so started with this small scale integration having 10 to 100 number of transistors per chip. Then in 60s to 70s, so it switched over to MSI, medium scale integration. There we have got 100 to 1000 number of transistors per chip. Then came LSI, large scale integration, having 1000 to say 10,000 or slightly more number of chips. And after that, when we incorporate more number of transistors onto a chip, so that actually brought the era of VLSI. So, what has happened over the years? Over the years, number of transistors per chip has become more and more complex. As the VLSI manufacturing process is advancing, the technology is advancing, size of individual transistors are becoming small. So, on the same silicon floor, so we can accommodate more number of transistors. So, if we can accommodate more number of transistors, then we can have more complex systems and we can put more functionality into the system. So, that way our IC chips are becoming smaller and smaller, and the devices that they are becoming the systems that we are developing around that. So, they are becoming smaller and smaller. So, it is captured by this Moore's law. It tells that ICs, the scale of ICs doubles every 18 months. So, every 18 months the number of transistors per unit area, so that is going to double. So, this law is more or less followed till today. So, in future technology what will happen, whether some new technology will come up to continue with this rule or not. So, that's a question being debated by the VLSI device manufacturers. So, we will not go into that, but whatever happens, so complexity of VLSI systems will continue to increase. So, that is accepted. Now, this increase in complexity, it poses important challenges to the designers. That is true, because now the system is more complex, etc. However, for the test engineers also this becomes a very important aspect. Now, you see, if you have got only say 100 transistors in the entire chip, so we can test them exhaustively. Possibly we can try to develop some test technique by which each of those 100 transistors can be tested individually. But if we do that, when I have got say lakhs of transistors on the chip, then this testing time itself will become too high to be accommodated into the overall system chip manufacturing time. In fact, it is true that in the overall VLSI design life cycle, about 60 to 70% time is spent on the testing part. So, if testing is not given proper care, then it may so happen that at the end, when we are trying to test the system for correctness, so you may find that many of the chips are failing. So, that may affect the performance of the manufacturing process, or that may lead to some loss in the profit of the company. So, this has got many complexities. So, with the course we will see how this complexity of testing has grown. Apart from the inherent challenge, that is number of devices or number of transistors per chip has gone up, the other issues that are there, it include the power consumption of the chip has gone up, because so many devices are there. So, in the testing phase also we need to address the power issue, we need to address the temperature issue, the different portions of the chip, so they become hot differently. So, as a result, as we know that as the temperature of a VLSI system, VLSI chip increases, its delay behavior becomes unpredictable. So, if different parts of the chip are heated differently, then the delay behavior of different parts will be different. As a result, some part may be showing that the signal may be reaching faster than the other parts of the chip. As a result, it may lead to some sort of timing errors. So, these are the things that needs to be taken care of. So, why testing is so important? So, Moore's law, it results from decreasing feature size. So, from tens of micrometer to tens of nanometer for transistors and interconnecting wires. So, this is the fact that has happened over the years to keep in accordance with this Moore's law. What has happened is the transistor sizes, so they have gone from micrometer to nanometer range, and it is decreasing further. So, interconnecting wires are also reducing in size. On the other hand, operating frequency, it is increased. So, it is from 10 kilohertz to 100 kilohertz to several gigahertz. So, the frequencies are increasing that way. This decreasing feature size, so it increases probability of defects during manufacturing process. So, what we essentially mean is assuming that my manufacturing process is my manufacturing process is flawless. So, there is no problem with my manufacturing process, but even then the silicon wafer onto which we are making the design, that wafer will have impurities, and that cannot be controlled. So, we cannot have 100% pure silicon wafer. So, when we are putting more and more devices onto the chip, the possibility of some of them becoming faulty, so that is increasing, because now that density is increasing. So, probability of defect during manufacturing process, this will increase. A single faulty transistor or wire will result in faulty IC. So, if we talk in terms of correctness of the IC, so this is the extreme point. So, a single transistor failing, it may result in the failure of the IC. A single wire failing may have to be considered as a failure of IC. Of course, there are techniques by which we have got fault tolerant designs and all that. So, I am not going into that. So, apart from that, in general this is true. Okay. So, now testing is required to guarantee fault free products. So, we want that this product should be fault free. So, how to ensure it? It has to be ensured by testing, because even if my manufacturing process is 100% correct, we cannot say with guarantee that the fabricated chip will be fault free because of impurities in the silicon. Plus, there are defects in the manufacturing process variations, etc. So, those cannot be we can never make the manufacturing process also 100% correct. So, testing becomes an important issue. There is a rule of 10 which says that the cost to detect the faulty IC increases by an order of magnitude as we move from device to PCB to system to field operation. So, when I have manufactured a transistor on the silicon floor, so we can test it. So, that transistor may become faulty. So, if that transistor is faulty, so we may think about replacing it by another transistor. There may be spare transistors to which we make the connection, just ignoring the faulty transistor. So, that way in the manufacturing process itself we can rectify the problem. Suppose we bypass that and take the device up to PCB level. So, in the PCB level we have got a number of such IC chips mounted. Now, if at that level I am testing, then my test is confined to the board chip level testing. So, a chip may be correct, a chip may be faulty. So, there is no question of having a part of the chip working correctly. So, that is not there. So, it may be PCB level testing can be done. So, device level, if we can detect some problem, we can rectify with minimum effort. If we have at the PCB level we have to replace the chip, or if we think about fault tolerance, then we have to duplicate that an entire chip that way. So, that way it becomes costly. Now coming to the system level, a system consists of a number of such PCBs, like a computer. If we open up the cabinet, you will see that a number of chips are mounted onto or number of PCBs are mounted onto the inside. So if something goes wrong, so there normally we do not have provision even to change at the chip level. So we have to change at the PCB level. So if the PCB is faulty, so we change the PCB. So that way it becomes testing. Now when it goes to the field, now there are many systems where we need to test the system when it has been put into the operation, particularly the safety critical systems. So there we have to do the testing, and if at that point the system fails, then possibly we need to replace it by another system altogether. So the cost increases as we go from the lowest level of devices to the field operation. So testing has to be performed in all these steps, all these stages, to minimize the cost or minimize the overhead. Testing is also used during manufacturing to improve yield. So it may so happen that in the manufacturing process, so we may find that in one lot of production there are many of the chips that are produced are not correct. There is it fails the testing process. So what it points to, possibly there is a problem in the manufacturing process itself. So to check the problems with the manufacturing process, so we need to do testing. So at the manufacturing stage itself we need to do the testing. So that is required, which is known as failure mode analysis, how what type of failures are coming in the manufacturing process. On the other hand, in the field operation also we need to do testing for fault free system operation. Like if we have got some safety critical systems mounted for medical purposes, okay. So those systems need to be tested while it is on in operation. So we need to test the system when it is operating. So that way, when the field operation also we need to ensure that the system is fault free, and if there is a problem that is detected in the system, so that has to be repaired whenever this fault is detected. So there may be several strategies for that. It depends on the system designer, like you may think about some duplicate or some replacement or some bypass mechanism in the operation of the system. So testing process, it looks like this, that we have got some circuit under test. You normally call it CUT or CUT, circuit under test. So this is the system that we want to test. So it may be at the very lowest level, it may be transistors and wires. At the highest level, it may be a system with some input and some output. So to test this system, what do? We apply some input pattern to this circuit under test, and as a result the circuit produces the output, and that output we need to check whether that response is correct or not. So this testing typically consists of applying a set of test stimuli. So maybe this circuit may have several types of faults in it. So a single input stimulus may not be sufficient for checking all of them. So it may be that one stimulus can excite only say 2 or 3 faults in the circuit. So to test for all the stimulus faults, so we need to have a set of stimuli. So all of them are to be applied. Okay. So depending upon the type of fault that we are going to cover, so or type of fault that we are going to detect, this stimuli part will also change. So stimuli part will depend on how it can be, how it can excite those faults. So these stimuli, they are input to the circuit under test and analyzing the output responses. So the response is produced here, and this response analysis has to be done. So if incorrect, then the CUT will be assumed to be faulty. If it is correct, then the CUT is assumed to be fault free. Now there may be several catches in it, like I apply say 100 test stimulus test stimuli. Now all these 100 test stimuli, they pass. Okay. So for the circuit produces correct desired output for all these 100 test stimuli. Does it mean that my circuit is absolutely correct? There is no problem with the circuit, but that cannot be guaranteed. Okay. So this only tells that the type of faults that this set of stimuli could detect. So, they were not detected in this system. So, that gives us this much this particular testing session will give us this much confidence. So, absolutely it is absolutely true that if I have to ensure or if I have to obtain very high confidence on the about the correctness of the system, then we need to apply a very large test stimuli. So, a set of test stimuli which is sufficiently large, but in the process what will happen is that the time requirement for testing, so that will go up significantly. In fact, we can if we plot it like this, on this side we plot the size of this stimuli set or number of test patterns that we are applying, and this side we plot the confidence, that how much confidence we can have about the correctness of the system. Then normally it shows a behavior like this. Okay. So, where if this is the say the 100% line, if this is say the 100% line. So, if you are applying a very small number of test pattern, if you are applying say only this much of test patterns, then the confidence that you are getting is only this much. So, you can say only out of 100 say may only say about 10% of the faults I have tested. So, I know that my circuit is secure against this 10% faults. Now, as you try to get more and more confidence, so you have to spend more time applying this test pattern and analyzing the responses. Accordingly, the cost of the system goes up, and in the because now for you know that if I have planned for producing some system, so it's if it may be that if the design can come within say 6 months, so less than so this is say 6 months. If the product can come within 6 months, maybe my profit will be very high. My profit will be high if it can come within 6 months. If it comes after this, after 6 months, it may start, the profit may start decreasing like this. Whether it will become 0 or not after some time, that depends on the product that we have, but this marketing team that can tell us that the product should come within 6 months for maximum benefit. Now, you think that if we want to put more time on testing, then this 6 months will not be sufficient. So, we need to put more time onto that. As a result, the benefit or the profit that we can get by marketing the product, so that will decrease. So, we need very efficient techniques for testing, so that my product can launch into the market within 6 months. At the same time, I have got very good confidence about the correctness of the system. So, normally we see that for similar type of products with similar functionalities, so products are there where the costs are widely varying. One of the major reason for this to happen is that this testing time that is dedicated to it is much less in case of cheaper products, because that saves the time to market, and as a result we can bring the product into the market at a much lower cost. But at the same time, the confidence on the product will be very low, because it is possibly not tested thoroughly with all the functionalities of the system. So, that is a known fact. So, that is there. So, testing will ensure that we have more confidence about the correctness of the system. In the VLSI development life cycle, so this testing will come at various stages. First, the VLSI design cycle starts with the specification of the design. So, we tell what we expect the system to do in terms of some formal or informal technique. It may be that we do it in some hardware description language, VHDL, Verilog, etc., or it may be that we write it in some other specification technique, from which this conversion is done to this to the behavioral description or structural description of it. Then after this specification is given, it passes through some design process, and this design process will give me the corresponding design. So, basically it passes through some CAD tools from where we get the design. Now, at this point of time, what is the guarantee that the functionality that I had specified here has been translated properly into this? A typical example may be, suppose I want to design a counter. So, when I am writing the specification of the counter, so if it is a say mod 16 counter, then we can say that okay, we can write down a behavior that count equal to 0, and for I equal to 1 to 15, count equal to count plus 1. If count becomes 15, then count will be reset to 0. So, that way we can write in some hardware description language. Now, this when converted into a counter design, possibly, so it will have 4 flip flops in it, and then associated gates and all that will realize the same functionality. Now, what is the guarantee that this design that I have got consisting of flip flops and these gates, they really have the behavior of the specification of the counter that I had. So, this is actually done by this verification process. Okay. So, this verification process, if there is a design error, then this verification process will try to prove some properties of the specification onto this design, and if the design is incorrect, then those proofs will fail. And when the proof fails, these verification tools, so they can generate some counter example by which it can tell you that okay, this is false because of this reason. So, this way this verification can be taken care, this verification phase can take care of this design errors. So, design verification targets design errors and corrections are made prior to fabrication. So, if you can detect some error in the design process here itself, then that can be corrected, and much effort can be saved, much effort in terms of testing can be saved in the process. After the design phase is over, so it goes to the fabrication stage. So, now there is no more correction to the design that is possible. So, we are going to the fabrication where we have made onto the silicon wafer the individual circuit. So, we have fabricated the transistors, the links between them, etc. Now, at that point of time, we need to check whether the transistors have been fabricated properly or not. As I was telling, if we can detect this wafer to be faulty at some point at this early stage, some transistor to be faulty. So, we can remove this transistor from our connection pattern, and maybe we can use a substitute transistor for the purpose. So, this fabrication level, at this level we have to do a testing which is wafer level test, but the wafer level test, the basic problem is that at that point these wafers are open, look, okay. So, they do not have any protection, like they do not have packaging and all that. So, when it is not there, so they cannot tolerate voltage fluctuations or very high voltage, very high power, etc. So, they cannot tolerate all this. So, as a result, this wafer level test is very delicate, okay, and then we need to take some special care while doing this thing. But we cannot avoid this stage, because this will be requiring us to check the correctness of the individual devices that are fabricated. Now, once we have got the confidence that okay, my transistors are all fabricated properly and all that, so it comes to the packaging stage. So, in the packaging stage, we it will be the packaging will be done. So, now we will have this bonding of the chip, and this at that point also we need to check whether this packaging has been done correctly, the pins that are created, whether the pins are connected properly to the system or not. So, those type of checks are to be done. So, that test is also necessary at the packaging level. And for so after fabrication has been done, so we have got this individual devices checked. Now, at the packaging stage, so this pins will be attached, and then we check whether this packaging has been done properly or not. So, at that stage also the functionalities are to be checked. So, that is done at the packaging level. And after that, when the chip has been packaged, so we have to check for the overall operation of the system, overall operation of the chip. So, that is due to quality assurance, whether it meets all the requirement of the system or not. So, that is done by the final testing. So, all these remaining tests apart from this verification, so they will target manufacturing defects. So, this fabrication problem, packaging problem. So, all these stages, so they will be checking for the checking for manufacturing defects. So, as I told at the very beginning, a defect is a flaw or physical imperfection that can lead to a fault. So, a fault is like this, say if a line, if two lines are say shorted, so we say that these two lines, there is a bridge that has been created. So, bridge is a type of fault. Similarly, a line may be a line may get shorted with say the power supply line VCC. So, we say that the line is stuck at 1. So, that is one type of fault, but the actual problem that comes is basically a shortening of the power supply line with that particular line. So, that is the problem. Similarly, if a line is open at some point, there is a break at some point. So, that may be treated as high or low, permanently high or permanently low, or high impedance state depending upon the technology. So, that is also a type of physical defect, but in terms of testing, so we will model it as a fault. So, we will continue in the next lecture on this.